Hello everyone. In this video, we shall talk about exponential functions and its graphs. So what is an exponential function? An exponential function is a function of the form f of x equals a raised to x, where a is called the base of the function and x is the exponent. Now here, the base a and the exponent x are both real numbers. However, the base a is restricted to be a positive real number, where a is greater than 0, and a cannot be equal to 1. So this is because if we use a is equal to 1, then the function will become f of x is equal to 1 raised to x. So which means that whenever we substitute any value of x, whether it is negative, 0, or positive, the value of fx will always be equal to 1, which means that the function will just become the constant function y is equal to 1. Now, since the base is a positive real number that is not equal to 1, then the values of a will be divided into two intervals. The first interval is when the base a is between 0 and 1, and the second interval is when the base a is higher than 1. So examples of these exponential functions are f of x equals 2 raised to x. So in this case, the base a is equal to 2, which is higher than 1. Now, the second one is the function f of x equals 1 half raised to x, where the base a is equal to 1 half, which is between 0 and 1. Now, let's try to graph these functions. So let's have the graph of f of x equals 2 raised to x. And in this case, the base is higher than 1. So if we will be using the table of values and assign x to be negative 3, negative 2, negative 1, 0, 1, 2, and 3, these will be the y values of the function. Now, to evaluate an exponential function using these x values, we have the following. So, for example, if we have f of negative 3, this is written as 2 raised to negative 3. If we have f of 0, this is written as 2 raised to 0. And if we have x is equal to 2, then we have f of 2 is equal to 2 raised to 2. Now, this symbol here, 2 raised to 2, is actually the product of two copies of 2, and this will be equal to positive 4. Now, any number other than 0, when raised to 0, will always be equal to 1. So that's why we have this ordered pair 0, comma 1. And for 2 square equals 4, we have the following ordered pair. Now, if the exponent is negative, 2 raised to negative 3 can be written as 1 divided by 2 raised to 3. And 2 raised to 3 is the product of 3 copies of 2, which is 2 times 2 times 2, or 8. So this one can be simplified as 1 over 8. So that's why we have this ordered pair. Now, if we will plot all these ordered pairs on the Cartesian plane, we get the following graph. So when x is equal to negative 3, we have y equals 1 over 8. When x is equal to negative 2, y is equal to 1/4. When x is equal to negative 1, y is equal to 1 half. When x is equal to 0, y is equal to 1. When x is equal to 1, y is equal to 2. When x is equal to 2, y is equal to 4. And then when x is equal to 3, then y will be equal to 8. So in this case, if we connect these points by a curve, then we get the graph of f of x equals 2 raised to x. Now for the properties of this graph, now we observe that the graph extends indefinitely going to the left and going to the rightwards. So which means that the domain of this function is the set of all real numbers, or the interval from negative infinity to positive infinity. Now for the range of this function, if we substitute any value of x, whether it be negative, 0, or positive, the value of f of x or y would always be positive. And as you can see from our illustration here, that the graph lies above the x-axis, so which means that y is greater than 0, or it is the interval from 0 up to infinity. Now, since the graph lies above the x-axis, it never crosses the x-axis because of the value of y would always be positive, so it cannot be equal to 0. So which means that this graph doesn't have an x-intercept. Now, the graph crosses the y-axis at the point 0, comma 1. So the y-intercept is 0, comma 1. And then from left to right, the graph is increasing. And then if we want to check any asymptotes of the graph, so this graph doesn't have a vertical asymptote. However, since the graph approaches the negative x-axis, then there is a horizontal asymptote. And the horizontal asymptote is the x-axis or the equation y is equal to 0. And then also, this graph is, this function is a one-to-one function. So it passes the horizontal line test, which means that every horizontal line drawn on this graph will cross in a maximum of 1 point. Now next, let's consider this time the graph of f of x is equal to 1/2 raised to x. So again, before that, these are the properties that were listed down in the previous slide. So now, if we have f of x is equal to 1/2 raised to x, and using table of values, we have the following ordered pairs. So if we're using f of -3, this is evaluated as 1/2 raised to -3. And this can be written as 1 raised to -3 over 2 raised to -3. Now from algebra, we can write this as 2 raised to +3 over 1 raised to +3, which just gives us the value of 3. So using these evaluation of functions, we get the following points. And then plotting all these points on the two-dimensional coordinate system, we get the following. So when x is equal to -3, the value of y is 8. When x is -2, the value of y is 4. When x is equal to -1, the value of y is +2. When x is equal to 0, the value of y is +1. When x is equal to 1, the value of y is 1/2. When x is equal to 2, the value of y is 1/4. And the value, if x is equal to 3, the value of y is 1/8. So connecting these points by a curve, then we get this graph of f of x equals 1/2 raised to x. So for the properties, so all these properties or all the properties of f of x equals a raised to x when a is higher than 1 are the same with the properties of f of x equals a raised to x when the value of a is between 0 and 1, except that this graph is a decreasing function. So if you will notice, these are the properties for the base a between 0 and 1. So the only difference is that the function is a decreasing function. Now, if you notice that in both intervals of a, the graph or the function, the exponential function, is a one-to-one function. So this means that whenever we have the equation a raised to x is equal to a raised to y, this means that this equality will hold whenever both of their exponents are equal. So for instance, if we have 2 raised to x is equal to 8, this means that 8 can be written as a power of 2 or 2 raised to 3. So this would imply that x is equal to 3. So that's how we apply this one-to-one property of exponential functions. Now, so since you already know how to graph the basic exponential function f of x is equal to a raised to x. So this time, let's consider the graph of g of x equals a raised to x minus h. So the graph of g of x equals a raised to x minus h is just a shift of the graph of f of x equals a raised to x. Particularly, it's a horizontal shift of the graph. So if the value of h is positive, then the graph of f of x equals a raised to x must be shifted h units to the right. Now, if it is negative, if h is less than 0, then the shift must be h units to the left. So for example, let us graph g of x equals 2 raised to x plus 2. Now, x plus 2 here can be written as x minus negative 2. And this implies that h is equal to negative 2. So that means the graph of g of x is just a shift of the graph of f of x equals 2 raised to x by 2 units to the left. So in the next slide, we have the graph of the basic exponential function f of x equals 2 raised to x, and we use the following points of that graph. So since 2 raised to x plus 2 is just a shift of the graph of f of x by 2 units to the left. So from this point, we count 2 units going to the left to shift the points of the graph of 2 raised to x. So all these points here are the points of g of x equals 2 raised to x plus 2. So this is how you graph the exponential function 2 raised to x plus 2. Now, since there are shifts, there's a horizontal shift that happens, then that means the properties of g of x equals 2 raised to x plus 2 may differ with the properties of f of x equals 2 raised to x. Now, let's identify which properties will remain the same and which properties are different. So since the graph of 2 raised to x plus 2 is or is extending indefinitely going to the left and right, still the domain will be the set of all real numbers. And since the graph is still above the x-axis, the range will be the set of all y values such that y is greater than 0. And since the graph is shifted only to the left, then the x-intercept will be the same. So there's no x-intercept for 2 raised to x plus 2. However, the y-intercept will change. So in this case, if we substitute x equals 0 into the graph, into the equation, into this equation, then we get the value of y as 4. So that means that the y-intercept is 0, 4. So this red colored property indicates that the y-intercept of the basic function will change if there is a horizontal shift. And still, since the base is equal to 2, which is higher than 1, the function is still an increasing function. And then the horizontal asymptote will still be the same. It's the x-axis because the shift is only to the left or to the right. And it is also a one-to-one function. Okay, next, this time let's graph g of x equals 1/2 raised to x minus 1. So in this case, the value of h is equal to positive 1, which indicates that the graph of f of x equals 1/2 raised to x must be shifted by 1 unit to the right. So in the next slide, this light blue graph is the graph of f of x equals 1/2 raised to x. Since h is equal to 1, we will just shift all the points of the light blue graph by 1 unit going to the right. So these resulting points here will be the points of the graph of g of x equals 1/2 raised to x minus 1. So again, there will be some properties that will be changed, and in that case, it's the y-intercept. So the y-intercept here is 0, comma 2, and all the rest of the properties will be the same as in the basic function of exponential function. So this time, let's consider the graph of g of x equals a raised to x plus k. So the graph of this function is just a shift of the graph of f of x equals a raised to x. Particularly, it's a vertical shift, which means that the basic function a raised to x will be shifted upward or downward. Now, if k is positive, then the graph of the basic function must be shifted k units upward. If k is less than 0 or negative, then the graph of the basic function must be shifted by k units downward. So for example, if we will graph g of x equals 2 raised to x minus 1, in this case, k is equal to negative 1. So the graph of f of x equals 2 raised to x must be shifted by 1 unit downward. So to graph this 2 raised to x minus 1, we consider the graph of the basic function f of x equals 2 raised to x, and all the points will be shifted by 1 unit downwards, and so on and so forth. So we have this graph of g of x is equal to 2 raised to x and then minus 1. So now, if we apply a vertical shift of the basic exponential function, which of the properties will remain the same and which of the properties will change? So since the graph still extends indefinitely going to the left and to the right, then the domain is still the same. However, since the graph moved downwards, then the range will change and it will now be y such that y is greater than or is greater than negative 1. So in general, if we have the value of k, then the range will be y is greater than k. So since k is equal to negative 1 in this example, then that means our range will be y is greater than negative 1. Now, for the x-intercept, we know that the basic exponential function do not have an x-intercept. However, since the graph now moved downward, that means the graph will now cross the x-axis. So in this case, or in this particular example, the x-intercept is the origin. And obviously, it is also the y-intercept. So the range, the x-intercept and the y-intercept may change whenever we have a vertical shift of the basic exponential function. So since the base that we used in the previous slide is 2, which is greater than 1, then it is still an increasing function. And since the graph moved downward by 1 unit, the horizontal asymptote will also move by 1 unit downward. So originally, the basic function has a horizontal asymptote, which is y equals 0 or the x-axis. But since it moved 1 unit downward, the horizontal asymptote now will be y is equal to the value of k, which is negative 1. And still, it is a one-to-one function. Now, if we have the example g of x equals 1/2 raised to x plus 2, in this case, the value of k equals 2. So to graph this g of x, then we have to shift the graph of f of x equals 1/2 raised to x by 2 units upward. So if we have the light blue graph as the graph of f of x equals 1/2 raised to x, all the points on this light blue graph will be shifted by 2 units upward. So all these points here are the points of g of x equals 1 half raised to x plus 2. So for the properties, so just like in the previous example, um, some of the properties may change, and that would be the range. So since k is equal to 2, then the range will be y is greater than 2, and the horizontal asymptote will now be y equals 2, no, since k is equal to 2. And then in here, the x-intercept is none because we move vertically upward. So definitely, there's no x-intercept. But the double star here means that whenever we have a vertical shift, it's possible that there will be an x-intercept. So just like in the previous example. And then the y-intercept will also change. And in this case, if we substitute 0 to x, then we have 1 half raised to 0 is 1. And then adding 2 will give us 3. So that's why the x-intercept is 0, comma 3. So all the rest of the properties will remain the same. So the domain will still be the set of all real numbers. It is still a one-to-one function. But since the base k that we used in this example is 1 half, then it is a decreasing function. Now, so if we will combine these horizontal and vertical shifts, then we have the function g of x equals a raised to x minus h plus k. So the graph of this function is just a shift horizontally and vertically of the graph of f of x equals a raised to x. So to graph g of x, we use the value of h to shift the graph to the left or right by h units, and then the resulting graph must be shifted again by k units, either upward or downward. So for example, if we have the graph of g of x equals 2 raised to x plus 2 minus 1, in this example, x plus 2 can be written as x minus negative 2. So this indicates that the value of h is negative 2. And since we have a minus 1 outside of the exponential function, then k is equal to negative 1. So therefore, the graph of f of x equals 2 raised to x, where the graph of the basic exponential function must be shifted 2 units to the left, then followed by a shift of 1 unit downward. So here is the graph of the function. So we have this basic exponential function. So the graph shall be, or the points shall be shifted by 2 units to the left, and then followed by a 1 unit shift downward. So that's why we have those blue points. Okay, so the blue points here are the points of the function g of x is equal to 2 raised to x plus 2, and then we have minus 1. So for the properties, we have the following. The domain is still all real numbers. The range is now y is greater than negative 1 because k is negative 1. And then x-intercept and y-intercept will change. So since we move downwards, we move by 1 unit downward, then there will be an x-intercept, which is negative 2 comma 0. Then the y-intercept is 0 comma 4. It's still an increasing function because the base is equal to 2, which is higher than 1. And then since k is equal to negative 1, the horizontal asymptote will be y is equal to negative 1, and it is still a one-to-one function. Okay, now this time, let's consider the graphs of g of x equals a raised to negative x, and g of x is equal to negative of a raised to x. Now, the graph of g of x equals a raised to negative x is just a reflection of the graph of the basic exponential function along the y-axis, while the graph of g of x equals negative of a raised to x is just a reflection of the graph of the basic exponential function along the x-axis. So for example, if we are going to graph, let's say g of x is equal to 2 raised to negative x. So observe here that this black graph here is the graph of the basic exponential function. So since the exponent is the negative, then we shall reflect all the points from the black graph along the y-axis. So which means that this will be reflected along this y-axis, and then the mirror image will be this point. And this point will be reflected along this y-axis, and the mirror image is this point. Now this one is still the same. So we don't, since it is on the y-axis, it will not be reflected anymore. It will stay as is in that same position. Well, this point here will be reflected, and the mirror image is this point. Well, this point will be reflected here, and this point will be reflected on here. So we have this graph of 2 raised to negative x. Now for f of x equals negative of a raised to x, then the graph of the basic exponential function will be reflected along the x-axis. So which means if we will extend this y-axis here, we have the following. Then this point will be reflected along the x-axis. So we have this point here. This point will be reflected along the x-axis. So its mirror image will be this one. And then this point here will be reflected along the x-axis. So we have this point here. And this point will be reflected going here. And then this one will be reflected here, and so on and so forth. So that's why we get this particular graph of g of x is equal to the negative of 2 raised to x. Now, finally, for exponential functions, so a commonly used base for the exponential function is the irrational number e, where e is approximately 2.71828188, and so on. So this function is denoted by f of x equals e raised to x and is called the natural exponential function. Now the graphs of f of x equals e raised to x and f of x equals e raised to negative x are shown in the next slide. So since e is is the base, which is approximately 2.71, so the base is higher than 1, which means that the graph is an increasing exponential function. Now the other one, the blue graph, since the exponent x is negative, then the graph of e raised to x is reflected along the y-axis to get this blue graph. So that these are the graphs of e to the negative x and e raised to x. Now the applications of exponential functions are as follows. So it can be applied in investing, particularly in compound interest. It can be applied in biology and chemistry, particularly the growth and decay of bacteria and some substances. And then exponential functions are applied in the population growth. And also in medicine, it is applied in the amount of medicine in the bloodstream. So this ends our video about exponential functions. So I hope that you learned something about this type of function. And please do not forget to subscribe to my channel. Thank you for listening.